from the from Sammy's China. Now in this talk, she will talk about primitive invariants from laminations. So let's give him a welcome. So,
So thank you very much for the invitation and the introduction, and thank you for organizing this workshop, which I think it's a great idea. So today I'm going to talk about work that I recently posted at the end of July on the archive. You can find it. Basically, I'm going to go pretty quickly on the results because there are many theorems and statements that I made in this paper, but I tried to select a few for this workshop. And you can find all proofs and extra statements in the paper, and you can always contact me if you want more details. So this work is based on the intersection of three different fields: geometric topology, algebraic geometry, and geometric group theory. But in principle, this work is at the heart, is at the
sorry, Veronica.
beginning.
Sorry, can you
Yes.
please close the mini window that appearing on your screen?
Okay, I'm not sure that I can manage it. Let me see if I can manage. Um,
I think you just click the fourth button, like the fourth one, the very first one.
the very first. Okay,
Yeah, very
let's see if it
first one.
works. Okay,
Okay,
now
okay. And okay, okay. Yeah. All good, all good.
should be okay. Okay,
Yeah,
sorry,
yeah.
sorry about that.
No worries.
Um, so as I said, this work is at the intersection of three different fields, but in principle, this is just the first step of a much broader project, which lies at the intersection of differential geometry and geometric analysis, where essentially integrable systems might arise. And so for this reason, it could be of interest to this audience. So I'm going to explain how these three appear in my project and why the future directions are in this realm. So the outline is as follows. I'll first introduce Gromov-Witten invariants. I'm going to be very pedagogical, but I think it's useful to keep it in mind to see what are the ingredients that we need for this analysis. Then I'm going to talk about nodal curves and delinear-Mumford moduli spaces, which are the particular setting of my analysis. And then I'm going to introduce primitive invariants, which have only recently been rediscovered in the context of calculation of Gromov-Witten invariants. And I'm going to explain how they basically arise in the context of geometric topology. Then I'm going to specify the analysis from a geometric group theory point of view, in particular from the monodromy and mapping class groups. And then I'm going to go back to algebraic geometry by means of the construction of symmetric obstruction theories and why are these important to consider together with geometric group theory and laminations appearing on manifolds. And then I'm going to conclude and giving you some outlook on future directions. So basic thing, what are Gromov-Witten invariants? Essentially, they allow us to count curves in a certain variety. Now, this curve counting is usually addressed in the terms of enumerative geometry. And there are many different techniques that have been developed throughout the years because different varieties require different methods, different mathematical tools. And to date, there's still no well unified procedure to calculate these invariants in all types of varieties. So you need to specify according to the setting that you are analyzing. But this open problem is actually prompting people to find a unified framework. So my analysis that I'm going to explain today is showing a different perspective where this possible unification could come from, which is from geometric group theory and geometric topology, in particular through the use of laminations. So essentially what I want to explain for those who've never seen Gromov-Witten invariants before, this is what I want to describe. Say that I have some variety, which is this black box. It could be, for example, a Calabi-Yau, and I start with a certain curve, and the curve might not be a continuous object or smooth object. Essentially, it's this curve that I draw here, and the blue curve and the dots. I could have this as a starting point, and I want to say, I want to find a way to count how many of these curves can be found in the variety X. Now, basically, I'm going to explain how this picture comes up, but much later. This is just to give you an idea of the picture. Now, so essentially the main point in doing this, to count these curves, we need to find a suitable parameterization to embed this curve in the variety. So this parameterization is the choice of this map F that maps from Riemann surface sigma to the variety X, such that when f is restricted to sigma, it gives back the curve that we started with, which is the blue curve C. In particular, we want to restrict the analysis in the case of nodal singularities. Now, where the curve has nodal singularities at most, which means that is the worst possible scenario that we want to consider, because in principle there could be much stronger conditions to impose, but for the time being, this is what we are going to focus on. Now, nodal singularities arise when you consider, for example, moduli spaces of a certain kind. I'm going to show you how these nodal curves come up. So before that, we start from a curve. I said you take a continuous curve and you take some additional points, these x from x1 to xn, and we assume this curve to be stable. The stability of the curve means that it has finitely many automorphisms, these H automorphisms that map the curve to itself, such that this diagram commutes. F is the same F that I defined before, which is the parameterization of the curve. So this diagram has to commute to ensure that the curve we start with is stable. Now, given this stability condition, we can define a moduli space, and this is what I define as being m bar gn over x, which counts all these possible f's. But in principle, this can be further refined by adding some extra condition, in particular by choosing some beta, where this beta is an element of H2 of X, and by requiring F to be stable. Sorry, this is a typo. Yeah, I should have said F is stable, of course. Now, to see where nodal curves actually come from is, if you want to consider how many curves we have in M10, so which means a moduli space with genus 1 and 0 punctures on P2 with degree 1 curves. Now, this moduli space would look something like this, which means you have a genus 1 part, the red one, and a genus 0 part that are touching at one point. So this would be in P1, okay? Now, if you map this to P2, the genus 0 part would be this black line, and the genus 1 part would be this point. Now, the overall dimension of this curve would be, of this moduli space would be 4, because you would have 2 dimensions coming from the genus 0 part, and 2 parts coming from the elliptic curve, obviously, because one is coming from the point and one is coming from the modulus in the elliptic curve. But if you did this without using Gromov-Witten invariants, you would end up having the wrong answer. Because of that, essentially all the techniques that were known to do curve counting before Gromov-Witten invariants would have led to the wrong answer in this particular example. So this is why we need this formalism, even if it appears much harder to understand. So now I'm going to go towards the effective definition of the Gromov-Witten invariant. So you start from this moduli space that I defined before, using these stable curves and specifying a particular cohomology class to count holomorphic curves in X. And you define these evaluation maps that come in N. There are N of these, because one is for each puncture. And these evaluation maps essentially take the stable curve that you start with, and you map it to F evaluated at one particular puncture. And then you consider a subvariety of manifolds inside your original variety. So you take V1 to Vn inside X, and the homology class of each one of these varieties is going to have some Poincare dual that I call gamma I, which lies in the cohomology of X. Now, considering the cohomology of taking the pullback of the evaluation on gamma I, you take the total cohomology class to be the union of all the evaluations pullbacked on each Poincare dual. And this is going to be the integrand of a quantity, which are some correlation functions that are so-called Gromov-Witten invariants. So the Gromov-Witten invariants need as input some cohomologies, and they have to be integrated over a virtual fundamental class, which is this that I define here. Now, the reason for the virtual, in principle, you could integrate over the moduli space without considering the virtual part. The reason we go to the virtual part is when we account for moduli spaces that are not smooth, which goes exactly to to the example that I showed you before, where nodal curves arise, in that context, you need to go to the virtual part. Otherwise, you would just get a trivial Gromov-Witten invariant. So this is for accounting for the non-triviality. If you want to know more about this, there's a lot more to be said because, for example, you could think of, if you know that the moduli space arises from some quotient of the Teichmüller space by the mapping class group, this virtual analysis is associated to looking at the virtual counterpart of the mapping class group, which is needed whenever we deal with things that have torsion. So when you have torsion involved, you always need to get to the virtual mapping class group, and the associated class that we are integrated here over is exactly associated to that virtual mapping class group. But the most important thing, even if so this is essentially the tool that we use to calculate these curves, how many curves there are in a particular variety X that satisfy this stability condition. So the advantage of using this method is coming from the properties that the moduli space that is described in this manner satisfies. And in particular, there's one major property, which is this forgetful map, that it's a property of the linear-Mumford compactifications, and it's essentially that it forgets the n plus first point puncture. And this forgetful morphism is very important even if you take the differential geometry perspective and you try to calculate things like the energy around the necks that then shrink towards punctures that are exactly the punctures that we're dealing with when we talk about the degeneracy of the curves. So there's a lot more to be said in this regard, but it goes towards a different field. But essentially, this is the major point, the fact that you can reduce the number of punctures without losing information about the moduli space. And this is a highly non-trivial statement, okay? It's an oversimplification for sure. In fact, part of my analysis, which I'm not addressing in this talk, is actually going to address the case where this forgetfulness cannot be made, okay, because there are some cases where it doesn't hold. So the delinear-Mumford space, as I mentioned, is exactly this moduli space. This is just an extra definition I'm providing, but it's the set of all isomorphism classes of the curve that I started with, of genus G with n-punctured curves. So this projection map, this forgetful map, is exactly a crucial property of the delinear-Mumford compactifications and collapses unstable components to points. So what do these nodal curves look like from the moduli space perspective? I already gave you an example before when I showed you the moduli space of genus 1 and 0 punctures on P2 with degree 1. Now, this is another picture that I'm showing here. It's got higher number of punctures because we're going now towards the calculation of Gromov-Witten invariance in this context. So there have been recent developments in 2021 by Arbuts, Pierrick Bousseau, Pandaripande, and Zvonkin, who addressed the calculation of Gromov-Witten invariance for complete intersections in projective space. And the reason why this is a crucial thing is because this is where cohomologies, primitive cohomologies arise. Now, primitive cohomologies essentially is a broader set with respect to ordinary de Rham cohomology. They account for the fact that whenever you have a variety which is embedded in an ambient variety, the cohomologies described in the embedded manifold are going to have some contribution in the cohomology which comes from the ambient space, and some other part which is intrinsic to the variety itself, so it does not have anything to do with the ambient space. Now, from the point of view of the moduli space, you can actually see where these cohomologies would arise. As I mentioned before in the definition of Gromov-Wittens, whenever you have punctures, you need to dress them with some cohomology, and those cohomologies in that definition were just the usual de Rham cohomologies. But whenever you have these complete intersections in projective space, the cohomologies need to be dressed in a different way. In particular, if you look at the picture on the left-hand side, there are different types of punctures. I have black punctures, which are the ordinary ones that would be dressed by the usual de Rham cohomologies, and then I have some red ones, these red points. Now, the red points actually tell you that these are nodes, as you can see from the picture, but at the same time, these come from replacements of primitive insertions. And so this tells us essentially that this curve comes from some variety that is an immersed variety in an ambient variety. So it's like saying it's describing a complete intersection in a projective space. And this is what my paper is all about. So essentially, you can think of these punctures as being zero length geodesics in a two-dimensional Riemannian surface, which is this one on the right-hand side. So the punctures that are in black would just be the curves that I see here on the boundary. And then I have the red ones that are actually like I can blow these up and they give me some extra laminations. So this is where the laminations in the title come from. So these red lines actually are extra circles that characterize my surface, and they are highly non-trivial. So essentially, primitive cohomologies, as I said, they come from analysis made in the past 15 years, I would say. From 2009, the pioneering work by Tseng and Yao, who did it in 6 dimensions, but then this was extended also to 4D by Gibson, Tseng, and Vidussi. And they analyzed this, especially in the context of follow-up work by McMullen and Taubes, who looked at 4-dimensional manifolds. Now we'll explain very briefly how these arise, because essentially you start from a Riemannian surface, sigma, and you take an element of the automorphisms of this Riemann surface, so sigma to sigma, which is an element of the mapping class group of the surface. And you combine these two elements, sigma and f, into a 3-dimensional manifold, which is called the mapping torus. Now, this mapping torus has a fiber and a monodromy. So then you take the product of the 3 manifold YF with an S1, and this leads to a symplectic 4 manifold, which inherits the structure from the 2-dimensional data we started with, which is sigma and f. So essentially, the 4 manifold, the symplectic manifold X and omega F, entirely comes from just the 2-dimensional data. And so when we try and map this to the calculation of Gromov-Witten invariance, the essential part to take away is that rather than having just a product that I showed you before, right? We had the union of the pullbacks of the evaluation maps calculated on particular cohomology insertions on the punctures. Now we're going to have some extra structure that comes from not just the round cohomologies, but also from the replacements of the primitive cohomology insertions, which are going to be some extra factors that we should expect to come to be accounted for in the integration over the virtual fundamental class. So now, the major point is that the calculation that Arbuz, Bousseau, Pandaripande, and Zvodskin did is that they calculated these without accounting for the punctures to depend on the symplectic form. So they didn't account for this, which is actually meaning that the calculation is much more simple. And from the topological point of view, it leads to less structure. I analyzed this from the geometric topology point of view, adding this dependence of the cohomology insertions to the symplectic structure. So essentially, I brought down the analysis of calculating the Gromov-Witten invariance to the analysis of this group homomorphism, which is from the fundamental group of the moduli space to the stabilizer of the mapping class group itself. So essentially, this is this is my analysis. This is where the whole paper, my paper, deals with. And basically, we see this coming from something which is already known in part, because we know that we can study the properties of the virtual cohomological dimension of the mapping class group by knowing about the critical exponent of a manifold obtained by quotienting the manifold, the original manifold, by some finite isomorphism group. You can think of this as being like the same as the moduli space obtained by quotienting the Tecmüller space with respect to the mapping class group. So the critical exponent is essentially a tool that has been used in the past already to provide upper bounds on the virtual cohomological dimension. And we know that the dimension of the virtual cohomological dimension is equal to that of the moduli space. So these are all ingredients that we need when we calculate the Gromov-Witten invariance. Here I added some extra details, which you can also find in the paper, which are generalizations of the systole function, because the generalized systole function is actually interpolating in between the injectivity radius and the critical exponent, which are these two things that we need to account simultaneously. Essentially, the calculation of Gromov-Witten invariance can be recasted to this interpolating function, and you can also find this in my paper. So it's a generalization of the formalism, because in principle, the ordinary Gromov-Witten invariance, not accounting for these primitive insertions, would just be equivalent to calculating on the critical points of some smooth function on a surface. And this can be seen, for example, if you consider these symmetric obstruction theories. So symmetric obstruction theories are essentially a tool that connect different branches of research. For example, in the context of homological mirror symmetry, they arise, but because they allow us to study Lagrangian intersections in symplectic geometry. But at the same time, they are very important for the calculation of Donaldson-Thomas invariants, which are an equivariant formulation of Gromov-Witten invariants for Calabi-Yau threefolds. This is because they arise as critical points of regular functions on smooth manifolds that I mentioned before. And one of these examples is precisely the systole function that I mentioned before on the moduli space. So we go back to basically the picture that I had before. We start with a variety and we have some moduli space for that variety, which we know to be singular. And the singularity needs to be resolved to calculate the Gromov-Witten invariance. But this resolution is a highly non-trivial step. And it requires imposing some constraints. And these constraints precisely come from this virtual cohomological dimension, which we need as a given element, a given data. And this goes back then to what I was mentioning before about the critical exponents and the injectivity radius, the interpolation in between the two, and the case where there's a singularity. So when you need to impose this for the case of singular manifolds, the resolution requires that you pick a particular point in the singular moduli space, and on that point you define a class actually of points at which you can calculate the Ext groups, Ext1 and Ext2. Now, this is essentially because Ext groups are a generalization of cohomologies. So you can think of this as being H1 and H2 generalized for that point. So this is important because it tells you that at most you would expect having cohomology up to degree 2. So with this, you can build a chart. And this chart is a diagram where you have the two Ext groups as the two coordinates. And the graph that you see here is essentially a plot of how you would expect the neighborhood of the point that you've selected, that I defined as being F, to change as you perturb the system. Now, this is why do we need this? And here we go back to the idea we had before. So remember, I had the curve. I had a blue curve on this hypersurface at one of the first slides. So we want to build the whole variety X just from that curve. So what I'm doing here, I'm precisely taking a point and I'm trying to see how much I can vary around that point without changing what I want to describe, which would be the moduli space of this variety. Now, this thing, if I can do that without changing too much the description, then I have chosen the correct parameterization, so I can also calculate the correct invariant. So that's the double check of this. Essentially, we wouldn't need to build this obstruction bundle if we had something like a Calabi-Yau, because this would be a trivial bundle. The non-triviality of the bundle comes because we have something which is not a Calabi-Yau, but it's an embedding. So we need to have something which is accounting for the singularity of the moduli space. And all this needs to be also in turn encoded in the degeneracy formula of Junli, which means that we need to calculate Donaldson-Thomas invariance and make sure that when we take and affine fibration of our variety, we need to make sure that the Donaldson-Thomas invariance and its generalized partition function factor through. I have to skip all this. So essentially, the main results that I have, that you can find the proofs in my paper, are that the virtual cohomological dimension of the image of fundamental the fundamental germ on the lamination that defines the primitive cohomology insertions has an upper bound provided by the dimension of PGN, where this is it comes from the reduction of the techumelar space on the Thurston spine. Calculated, it restricted the calculation on the class of the point where I'm calculating the invariant. These are extra theorems that I probably don't have the time to state because I'm already out of time. So I will just state this last thing, which is the upper and lower bound on the image of the map that goes from the fundamental group of the manifold to the stabilizer of the mapping class group itself. It has a lower bound when you account for having complete intersections in projective space. So essentially, primitive cohomologies introduce a lower bound on the image of this map, and this is one of the major results of my work. These are just extra things. And so future directions, as I mentioned, this is just a starting point of a broader research project, which is at the interface of calculating Gromov-Witten invariance in algebraic varieties and calculation of minimal surfaces in three manifolds. So this is why I'm currently collaborating with Professor Lynn Heller in Beams and her postdoc, which is at the intersection of differential geometry and geometric analysis. So having said this, I thank you for your attention and I take any questions there are.
All right. Thank you very much for Dr. Veronica's talk. So